So are there any questions from the previous lectures in graph theory? There are any we can just quickly discuss. I heard that there is going to be a tutorial on Sunday, so you can ask your questions there as well. But if there are any questions, like any specific questions that you think you want the PS to revisit in the tutorials, you can just write to us or also the PS. Right? I think they will mostly cover graph theory. But if there are any specific questions or you think like we should revisit some topic we have already done, we can do that in class also. You can write to us. Okay, so today we will actually look at a concept in graphs that's called matchings. Okay. So do any of you recall the definition of bipartite graphs?
Yes,
So what is a bipartite graph?
it can be partitioned into two graphs, all of which are all connected. Those parts aren't connected within them, but like aren't adjacent within them, but the whole graph is connected.
Right. So what do we mean by that? We have a graph G. It has partition. The vertex set is partitioned into two sets. One is U, the other is V, and then there are edges. But any edge is only from vertices in one partition to vertices in the other partition. So there are no edges between the vertices in the same partition. So for all E is equal to U, V, V, U is in U, and V is in V. Right? So when you draw this as a picture, you have two partitions, vertices on the left, let's call this the set U, and there are vertices on the right, which you call the set V, and there are edges from vertices in U to vertices in V. So among vertices in U or V, you disallow any edges. So this is what is a bipartite graph. That is, you can partition the vertex set into two, such that edges run from one partition to the other. So we will talk more about bipartite graphs today. But before that, we want to look at general graphs and understand what a matching is. Okay. So generally, if you look at certain applications in computer science or even in mathematics, you have these kinds of allocation questions, right? So what kinds of questions are these? For example, you may have jobs on one side. Let's say one partition is people, and the other side you have jobs. So for example, there can be plumbing, carpentry, some sort of an electrical work, some home interiors and so on. And then there are people on the other side. Let's call them A, B, C, D, E, and so on. And it might be the case that one person is trained to do 2 or 3 jobs, right? So A probably knows both plumbing and carpentry. B is good at both carpentry and like home decor or interior designing. D knows carpentry and electrical. And it might be the case that there are people who just know one, like they have one expertise. For example, C just knows electrical. He knows nothing else. That's his business. And you have to sort of allocate these people to jobs. This is a very natural question you want to do. And we want to design algorithms for this. For example, you have a set of people, you are also given a set of jobs. Even in a software company, this might happen. Like some people are good at coding, some people are good at testing, some are good at architecture and so on. So in a project, you will want to have a lot of people, each of them should be able to do most of the jobs. And you want, in essence, to complete all the jobs on the right-hand side, right? You don't want to miss out on any job. So you want to assign people to jobs such that in some sense, every job is completed. So maybe you can assign A to plumbing, B to carpentry, and let's say B also does, or B to home decor and D to carpentry. So now what is the issue with this? Like whatever I've drawn. This electrical work is left untouched, right? Like no, you have not assigned any person to do this. So intuitively, what you want to do is you want to sort of find an assignment of vertices, like the vertices in the right hand side, you want to assign vertices in the left hand side. such that for every vertex here, you wanted to have at least one vertex on the one pair on the left hand side. This is one application. We will define matches, but I'm just trying to motivate you. Similarly, you might have situations where you have like hospital beds on one side and then patients on the other side. Right? You might want to assign patients to beds. So you have like 100 beds here and you have like 5,000 patients here. You have to sort of find an assignment between patients and beds. So these kinds of applications, allocation applications naturally arise. And one such important application is the marriage problem. This is quite a well-studied problem in computer science. We will just like briefly describe this. We will look at matches and then come back and solve this problem. So the marriage problem is the following. You have men on one side and you have women on the other side. So on one side, you have men, on the other side, you have women. Let's say we have like A, B, C, D, E, 5 men, and then there are 3 women. Let's call them N, F, G. And in the general marriage making, what happens is, for example, A might have a preference. Right? He might be happy marry E or F, but he might never want to marry G. Such a preference he has. Similarly, B also has a preference. Like if at all I will marry only F. And C has a preference that I will marry G or I can marry E. And so on. So each of them submit their preferences. And based on this, you can actually draw a graph. Right? So you can put men on the left hand side, you can put all women on the right hand side. And if if a man is interested in marrying any of these women, you draw an edge between them. And this is what a marriage graph looks like. Now the goal is to find an assignment. So you have to pair men and women so that you are able to satisfy as many men as possible. Or you want to satisfy all the women. For example, for every woman here, you have to find a suitable match, someone who's happy marrying her. So these kinds of questions are very well studied, lots of research directions here. And we want to solve this problem. Right? So given a graph, we want to ask whether such an assignment is possible that makes every man happy or that satisfies every, like you look at every woman, you're able to find the match for her. Is this possible? Can you do this? So this is the marriage problem. We want to solve this problem. For this, we will visualize this scenario as a graph, as a bipartite graph. So this is clearly a bipartite graph, right? There is no way you're going to associate men to men or women to women. You're just going to draw it just between men and women. So from one partition U to the other partition U, you're drawing this. And we want to ask, when does a given graph have a nice stable marriage, right? When can you find correct relationships and match them? So you want to match them in such a way that every woman finds a man where there is an interest, right? So you should not put G, you should not force G to marry B because B is not interested in G. Okay? So this is what you want to do. So with this purpose, we will learn what are called matching sim graphs. We'll come back to this problem. So what is a matching in a graph? So matchings are defined for general graphs. So we will look in detail about bipartite graphs. So let us recall. So we have a graph G, which is a set of vertices and a set of edges. So now we are going to look at general graphs. Right? So you can think about these as simple graphs. For example, this graph. The matching M in G is a set of vertex disjoint edges. So we will mostly look at undirected graphs. So I will put G is undirected. Because it really does not matter, right? For our applications, what directions. We are just going to do some kind of an association. So it's a set of vertex disjoint edges. Right? So this is really motivated from this marriage problem. Like you cannot assign one woman to 2 men, right? So you want to find edges that are not, that do not share a vertex. So what do we mean by vertex disjoint edges? So these two, let me just number the edges so that it's easy for you. So 2 and 4, E2 and E4 are not vertex disjoint. Why is that?
They share a vertex.
They share a vertex, right? So this vertex. This vertex is shared by both E2 and E4. Whereas E1 and E3 are vertex disjoint. So now let's take this to be the graph G. Can someone construct a matching in G? Can you give me a set of edges that are vertex disjoint? A matching M in G. That's the question.
1, 5, and 3.
Okay, so she says this edge, and this edge. Is this correct? So this is a set of vertex disjoint edges, right? These three edges. So let me just so these three edges, 1, 5, and 3, they do not share any edge. So there is, so let me just write it down. So E1, E5, E3. Or more precisely, how we will write it is, usually we will number the vertices. I will follow the same convention. So you will generally write it as 1, 2, 6, 5, 3, 4. Okay? So this is a matching in G. Can somebody give another matching, a different matching?
Seven, 6, 2, 4.
Okay, so you're saying edges, right? The vertex numbers. So he says
7 and 2.
7, 6, and 2, 4. So this is also a match. So just put a different color. So he's there is no 7. What do you mean by 7, 6? You mean 1, 6?
1, 6, 1, 6. 2, 4 isn't edge. I meant 2, 3.
1, 6 and 3, 5 maybe. Okay, let me just erase off 1 second. I'll erase off the edge numbers so that things will come. Yeah, now can you say what was your choice?
Yeah, 1, 6, 2, 3 or 1, 6, 3, 5.
Okay, so 1, 6, 3, 5. So what you must see is that there are several matchings, right, in a graph. There can be several matchings in a graph. And some of them might have smaller cardinality than the others. So this is a matching M1 graph. This is a matching M2, same graph. And ideally, what we want to do is we want to maximize, right, the cardinality of the matching. Because you want to, even in these applications, you want to satisfy as many of them as possible. Like jobs, right? You want to complete as many jobs as possible. You want to allocate beds to as many patients as possible. So you will be generally interested in what is called a maximum matching. Okay. So what is a maximum matching? It's a matching in G of the largest size. So is the maximum matching unique? Let me just
In
add
this
it.
case,
In this graph it is, but in general graphs, let me draw one more graph. I hope this example works. Let's see. Correct. So here, how many maximum matchings are there in the graph?
you can either choose 4, 6 or 4, 7. So there can't be one max.
Right. So you can choose 1, 2, you can choose 3, 5, and you have two options, right, for this vertex. So you can either choose 4, 6 or you can choose 4, 7. So the maximum matching is not unique. Okay, so is this concept clear? If there are any questions, we should stop and we should take it. Because we will look at very hard questions on matching. At that point, you won't be in a position to revisit the definition of matching. Okay, so I assume that you all understand what a matching in a graph is. It's just a set of vertex disjoint edges. And you say that a vertex V is matched, or some textbooks use the word saturated by a matching M. If V is the endpoint of some edge, so this is what you mean by a vertex being matched, or sometimes this is saturated. So for example, if you look at this matching, right, the 1635 matching, is there a vertex that is not saturated?
Yes, 2 and 4.
Right, so 2 and 4, they are not saturated. So there are 6 vertices, but here only 4 vertices are covered. Whereas in M1, every vertex occurs. Right? So every vertex is saturated by M1. So let us just record this. So every vertex is saturated or matched by M1, but not the case with M2. Is this clear? This notion of a vertex being matched. So this is very important, that we can say whether a vertex is matched or not just by looking at the graph. We will also need the matching. So given a graph and a matching EG, I can ask whether a particular vertex is matched by that matching or not. So this is important. This by a matching. Is this clear? Yeah, if there are questions, we should take it. Okay. So now, what is the goal in the marriage problem or these job assignment problems? Now, can you rephrase this question in the language of matchings? So you have people, you have jobs, you have, let's say, more people, but you have only 4 jobs and they want to finish all these 4 jobs. So what is the question that we are trying to ask? So let's call this graph G. It has U, V, and E. Okay? So this is U, this is V. And then there are edges. Now, what is the question that we are trying to ask in the language of matches?
Maximal match. Or
We want to find a matching that saturates all vertices in V.
Okay, so does there exist? I'll come to the answer that somebody else gave. Does there exist a maximum matching? Why is that not the right question? Okay. Does there exist a matching in G that saturates every vertex in V? Is the question clear, everybody? Otherwise, we will just stop and use. Okay, so now such a matching in the terminology of matchings is called a perfect matching. So perfect matching in a graph is a matching that saturates every vertex. So it's perfect in the sense that you have already achieved what you want. For example, let's just try to see. So A to plumbing, B to carpentry. Okay, so A to plumbing, B to C to electrician. So this is a perfect match. Just draw it in a different color. This is a perfect matching that saturates. Is this clear? So now, what is the difference between a perfect matching and a maximum matching? Somebody had said that we can actually frame this question here as, does there exist a maximum matching in G? Why did we frame this as a matching that saturates every vertex in G? So in the language, this is the same as asking, does there exist a perfect matching? So there is one small which in the way I've defined it. So we are saying that it has to saturate every vertex, right, in G. When we do this for bipartite graphs, the left-hand side might have far more vertices. Like, for example, there might be like 100 people here and 4 jobs here. So whenever we say perfect matchings in bipartite graphs, usually we only want to saturate the smaller set. Right? The larger set anyway has so many people, so that is not possible. If there are 10 people here and 4 people here, you cannot expect a matching to saturate all the 10 people. Then there will be edges that are not vertex disjoint, which will contradict what a matching is. So the general rule, you have 2 sets, one set is much larger than the other, you want to saturate only the smaller set. Okay, that's what we mean by perfect matching. So some abuse of notation, but is the remark clear, whatever I said in the end?
Yes, ma'am.
Okay, so that you must keep in mind. Okay, so now what is the difference between a perfect matching and a maximum matching? What do you think? Is every perfect matching maximum? So when we talk about perfect matchings, right now we are looking at undirected graphs, not bipartite graphs. Let's just look at normal undirected graphs, graphs of this form. Okay? And if you look at a perfect matching here, for example, this one, okay? Is it a maximum matching?
Yes, ma'am.
Because it should involve all the vertices, right? You cannot do any better. So every perfect matching is maximum. But is every maximum matching perfect? So if I find a matching of the largest cardinality in the graph, for example, let's look at this. So this is a perfect match. This is a maximum match, right? That is the matching 1, 5 and 2, 3. So the maximum matching here has cardinality 2. And this is one such matching, but it is not perfect. There are vertices that are missed. 4, for instance. So maximum matchings need not be perfect, but perfect matchings are maximum. Okay. So now we will get back to whatever we were doing. We will only look at bipartite graphs. So for the rest of the lecture, we will only look at matchings in bipartite graphs. So what do we have? We have a set of, so we have a graph G, which let's call this U, W. I'm just using U, W to be consistent with the notes. That's okay. You won't mind. And then there is another partition. And then there are edges. Now the question is, by looking at this bipartite graph, can you decide whether it has a perfect matching or not? That's the question we want to ask. Just by looking at the graph, can you say, let's say there are like 10 vertices on the, let's put this as W, and this as U. There are some 100 vertices in W and 5 or 6 vertices in U. You want to ask whether there exists a perfect matching or not. So the question is, when does a bipartite graph have a matching that saturates you. So is the question clear? So this is the question that we will study in the rest of the lecture. Yeah, if you haven't understood any concept until now, you have to ask questions. Okay. So now, just before going forward, I'm going to introduce one more small definition. It's called the neighborhood of a vertex. Sorry. So it's usually denoted by n of v. So if you call this vertex, let's call this v, then it is exactly what you would think as the neighbors of v, those vertices that are adjacent to it. So these three vertices form the neighbors of v. So these three guys. So the neighbors of a vertex are the set of vertices, neighbors of v, set of vertices adjacent. For example, what can you say about the neighbors of 3 here?
Two and four.
These two, right? So these form the neighbors of 3. The neighbors of 1, for instance, are these two, right? 2 and 5, and so on. So definition of neighborhood should be like really clear. So those set of vertices that are adjacent to V, and in general, for a bipartite graph, if the vertex V is in U, then the neighborhood of V is a subset of what? W. Right? Because we don't have any edges within U. But in general, this might not be general graphs. But because now we have partitioned the graph into two sets, you know that for any vertex V in U, the neighborhood of V is contained in W. So now we want to understand with this definition, let us see. Right? When does a bipartite graph have a matching?
Hello, ma'am.
Hi.
Ma'am, by adjacent, you mean connected, right? Or is it anything else?
No. So there should be an edge between this vertex V and that vertex in the neighborhood. So what do you mean by connected? Okay.
Oh, okay. So I mean, with the vertices with which one is connected, then that set of edges are actually adjacent to one, right?
Yeah. So you should not use the term connected. So connected means what? For example,
So I mean, 1 and 2 have a edge between
edge,
them, and
right?
1 and
Exactly.
5 have.
Right. So what is the neighborhood of 1? It is, so this is a set of vertices, not edges. So the neighborhood is a set of vertices. Right? So
Okay,
what
okay,
is the
okay.
neighborhood of 1, 2, and 5?
Okay, okay.
Because so it is a set of vertices that are adjacent to. When you say connected, you should be slightly careful because, for example, 1 and 3 are connected, but 1 and 3 are not adjacent, right?
Yes, ma'am. Yes.
Right. So it's a set of vertices that are adjacent. Yeah, if there are any questions about neighborhood, it should be like damn clear right now. Going beyond this without understanding neighborhood is just pointless. You can just leave the meeting actually. It's not clear. Okay, so I'm going to assume that we all understand what the neighborhood of a vertex is. So now I want to answer this question. When does a bipartite graph have a matching that saturates you? I'm going to give some examples and I want you to come up with a solution to this. Okay, so let me draw some examples for you. So these are two partitions. I've drawn this earlier. Put this right. Okay, so does this graph have a matching that saturates you? So this is one partition, this is the other partition.
No, because B and C, like there's only 3 that can go to.
So,
that can be matched with either B or C.
okay, so does anybody else see why what she's saying is right? Just to be sure. So what she's saying is, okay, so suppose there is a matching that saturates all of, so this is U and this is W. And what do we want? We want to ask, is there a matching of size 4? Anybody else who's able to see this? Just to be sure that you all understand it. So if there is a matching of size 4, all right, so then for each of these vertices here, you must find a neighbor, right? And these edges should be vertex disjoint. That's what we mean by a matching. So for A, let's say I will choose 1. For D, I will choose, let's say 5 or maybe even 4. Now when it comes to B and C, B also has neighbor 3 and C also has neighbor 3 and I have no other options, right? So if I choose 3 to be matched, if I match 3 with B, I cannot match anything with C. Or if I match 3 with C, I cannot match anything with B. So what she was trying to say is that if you look at these two vertices, they have just one neighbor here, which means that there does not exist a matching of size 4. Is this clear to everybody? So in essence, what she's saying is if you look at this set of vertices BC, and if you look at the neighborhood of X, so what do we mean by neighborhood of a set of vertices? The set of neighbors of every vertex in that set X. So you have to look at, so this is neighbors of B union the neighbors of C. So if you look at X, this has cardinality 2. If you look at the neighborhood of X, this has just cardinality 1. So you cannot match in the sense that for these two of them, there's only one neighbor. So you have to choose 3 to match either with B or with C, in which case one vertex will be unmatched. Is this clear? Any questions? Then we will take this example. Okay, so I'm going to assume that there are no questions. Let's just look at another example. So does this graph have a matching of size 4? One set, this is the set.
Yes, ma'am.
So can you say the matching?
1B, 2A, 3D, and 4C.
Does everybody get that this is a matching and it saturates A, B, C, and D? So this is your U. Is this
Yes,
clear?
ma'am.
Okay. So now we understand what matchings are. We saw one example where a matching cannot exist. Okay? So from this, can we somehow get a condition, okay, for when a matching can or cannot exist from these examples? So clearly, if there is one subset here, okay, whose neighborhood is much smaller. So if you have a subset of size 2, such that its neighbor has size 1, then you cannot find a match. Okay? At least this much takeaway should be clear from these examples. So now we will come to the celebrated Hall's theorem. I'll write it for you. It's exactly what we learned from these examples. So let G be a bipartite graph. So we have G, which is U, W, and a set of edges. Okay? With U being the smaller set. Coordinate U less than or equal to coordinate. Then G contains a matching of size, the coordinate of U, if and only Can someone fill this? So first of all, it is strong in the sense that it's a necessary and sufficient condition for a graph to have a perfect matching. It's one of the most celebrated theorems in graph theory. Like probably this will be the best theorem the proof you will see in discrete math course. The proof of this theorem. But can someone try to just fill it up from this example?
If there's any group which has a like subset which has exact, move that set and induct.
If there is any subset, actually I could not hear the entire sentence.
Like if if there's any set X such that neighborhood like hood of X is the size of neighborhood is equal to the size X, then you can just ignore X and induct on the remaining and do it on X itself.
Okay, so when so it does not have a matching, there is some subset of the vertices in U whose neighborhood is small, right? That's what you're trying to say.
No, I'm saying that is fine. Now we want to prove like the only if part, right? Like it does have a matching then. So I'm saying
Right.
that if there is a set which has exactly the right number, like X has exactly X number of
But it can have more also, right?
if there is a set which has exactly that number, then we can remove it. Is all
No,
I'm
I'm
saying.
not asking for a proof. We are just trying to state the theorem.
Okay.
So
Okay.
what is the criterion on the right hand side? That's what. Yeah, the proof will be inducted. We will see that. So the point is, the observation is that if there is any subset of U that whose neighborhood has smaller cardinality than it, then a matching cannot exist. So matching can exist if and only if for every, yeah, what he said is right. He's coming to the proof, but we will see that slowly. For every subset S of U, the cardinality of S is less than or equal to the cardinality of neighborhoods. Is the statement clear? So now
Yes.
one small notation just to make my life easier is that if this is true, right, that is for every S subset of U, the cardinality of this set is much lesser than the cardinality of its neighborhood, then we say that G satisfies Hall's condition. So we call this Hall's condition. And we say that the graph satisfies Hall's condition. So a bipartite graph G satisfies Hall's condition if this is true. This is just to make the proof easy for me to write down. Okay, is this clear? This is just terminology, but still I want to make sure. Okay, so now we have to get into the proof. But is the statement clear? I just want to ensure that the statement is clear before moving on to the proof.
Yes, ma'am.
Okay, so then let's look at a proof. So just as he mentioned, there is an if part and there is a only if part. Let's do the easier part first. Okay? So let us assume that the graph has a matching of size U. So there are two parts. One is if G has a matching of size U, then G satisfies Hall's condition. The other direction is if G satisfies Hall's condition, then G has a matching of size U. So what do we want to show? If the graph has a, let's call this matching N. So if the graph has a matching of size U, then for every subset S of U, if you look at the cardinality of the set, it should be larger than the cardinality. It should be smaller than the cardinality of the neighborhood. So I want to just introduce one more terminology here, which will be useful later on. That we will usually subscript this N by G. That is whichever graph we are looking at. Because going forward, we will look at more graphs. So at that point, I don't want this to come up. So what does this mean? This means the neighbors of the vertices in S in the graph G. Okay, can someone see why this should be true? Let's say if there is a subset of vertices, subset of U such that the cardinality of S is greater than the cardinality of its neighbors.
Then we can't, we'll run out of the neighbors.
Right. So then then M could not have saturated. Saturated, all of you, right? Is this clear? It's exactly what comes up from this example. You knew that there is a matching M. So this matching M actually saturates all the vertices, right? But if you look at this set S, and this set has larger cardinality than its neighbors. So just by looking at this set, you can say that how did M satisfy this both these vertices? It is not possible, right? Because the set of neighbors itself is smaller. So this is a contradiction to the fact that M is a matching. So if G has a matching of size U, then G definitely satisfies Hall's condition. Is this clear? One direction?
Yes,
we can actually go over this if it's not clear. So now let's look at the other direction. So the other direction is probably the most important, tricky, interesting direction. If G satisfies Hall's condition, then G has a match. Of size. Okay. So the proof is by induction, what we call the strong induction. So does anybody recall what strong induction is?
Assume it's true for all things less than your current N.
Then if it's true if the predicate is true for all values less than N, then you can show that it's true for N. Right? Not like N to N plus 1, but for everything less than N to N plus 1. Less than or equal to N to N plus 1. So we are going to do a strong induction on the cardinality. Yeah, just to be sure. So far everything is clear, right? I see only like few people answering, so I just want to ensure it's clear to the others also. Maybe somebody who hasn't answered yes should just unmute and say yes.
Yes, ma'am.
Okay, fine. Okay, so now what is the base case? Let's just write this. Then there is just one vertex. So can somebody say a proof of this? There is just one vertex, and let's call this vertex V in U. Right? So you have U, the set U that has just one vertex V, and there is this set W. I'm just using UW because we are going to use this little v for vertices. Okay, so now what can you say? What does it mean what are we trying to show? That if G satisfies Hall's condition, then there is a matching. So we know that this graph G satisfies Hall's condition. So this singleton set containing the vertex V has a neighborhood that has larger size, right? So if you know that there is a neighbor here, let's call that little w or something. And this edge is in G, right? So now what can you say? I want to construct a matching of size 1. What is that matching?
Just match it to its neighbor, any neighbor.
VW, right? No, what do you mean by any neighbor? You know that this is an edge, so you just put VW.
Yeah.
Want to write down an explicit. Yeah, that is true. It might have more things here, so you put one of the neighbors is what we say. But I want to write down explicitly, so I'm going to say VW. So this is a match of size 1, and 1 is small. So the base case is done. Now for inductive hypothesis, we have to assume that it is true for all values below a certain number. Okay? So let's just look at the graph G. We are going to say that for all graphs G, U, W, E, with the cardinality of U less than K, if G satisfies false condition, then G has a matching. Size. Is the hypothesis, inductive hypothesis clear? So this is a strong induction. You can just look at it here. Right? For all U less than K, we are saying. So for any bipartite graph with the smaller partition having less than K variables, we are going to assume that if G satisfies false condition, that is, if you look at any subset and size of the neighborhood is greater than each size, then G has a matching of size. We are going to use this to do an induction. So now for the inductive step, what we have is a bipartite graph G. And what is the cardinality of U?
K.
Okay. So one thing we know is that the cardinality of U is greater than 1. Right? Because for U equal to 1, we have taken care of that. So we can assume that U is greater than 1. So it has two vertices. Definitely it has one vertex. So let's call this vertex. So let me just put a reference picture here. So there are these vertices in U. There are more vertices in. So there is one thing I must mention here. Okay, let me just finish the picture. Just drawing some arbitrary lines. So even in inductive hypothesis, we are going to assume that U is the smaller partition. Otherwise, it does not make sense, right? We want to match the smaller partition. We want to only saturate the smaller partition. So we're going to assume that U is the smaller partition. Okay, so this is the graph. You have U on one side, you have W on the other side, and then you have some additional vertices edges. And U is the smaller partition. And because the size is greater than U, you definitely know that there is one vertex here, U. And this also has a neighbor, right? You know that G satisfies false condition. So what can you say about this? So G satisfies false condition. So can it be that U has no neighbors?
No,
No.
because
That is not possible, right? Because G satisfies false condition, the neighborhood of U should be at least 1. Must have at least size 1, because even that singleton set will be satisfied. So definitely there is one neighbor. Let's call this little w. Right? So now I know that there is, for this vertex U in G, there is a vertex W. Okay? So let me put G here. That is W is in the neighborhood of U in the graph G. Is this notation clear? Yeah, this is not clear with us. That is, you're looking at the neighbors of U in the graph G. This is clear. So now this particular edge we know is in the graph G. From this, what do we know? We know that there is a W in the neighborhood, and you can use it to match, right? So this means that you can put UW in the matching M. So in the, what is the goal? We want to ultimately produce a matching in this graph of size mod U. That is a final goal. We are going to assume that the graph satisfies false condition. And there are K vertices here. So the cardinality U is K. Now, we Let me just put this in a different color. So this we have matched, right? So this we have matched, U to W. Now I want to use the inductive hypothesis. What should I do? So U is anyway matched. So there is no point in doing further assignment for U, right? So U from this point, after it is matched, it's actually useless. And we are looking at perfect matches. So W also cannot be assigned to any other vertex. So this is not possible. We cannot add this to M anyway, right? Because we have added this to M. If we add, let's say A, W also to M, then we will get two edges that are not vertex. So that's not a match. So at this point, W and U are both useless. So what should you do? To use the inductive hypothesis.
Just remove them and consider the rest of the
Right.
smaller size.
Right. So what he's saying is anyway we have matched U to W. So we can just remove U and W from the graph and consider the subgraph. So consider. So how do you write this? From the set U, I'm going to remove the vertex U. And from the set W, I'm going to remove the vertex W. And you look at the corresponding graph. So this is how you write a graph G, where U is removed from U, W is removed from W. So what about the edges? Right, so W will have some other edges, right? What do you do with those? You actually remove all of them. So when we say remove the vertex, you remove this vertex and both the edges. Okay? But this vertex should remain, remember, because this vertex you haven't matched. So that vertex you cannot remove. You can only remove this vertex and the incident edges. Similarly, vertex U you should remove. You should not remove incident edges. For example, you should not remove this vertex because this will be used later on to match some other vertex here or here. So this is called, we saw this earlier, this is called an induced subgraph. Sometimes called a vertex induced subgraph. So you usually write only the vertices. You don't write down the edges here. You just write down what vertices are there in the subgraph. So H is the subgraph, where you remove U from the set U, W from the set W, and all incident edges. So in other words, every edge in H is an edge in G, and every edge in G is an edge in H. So after removal, whatever was originally there will be kept, except incident edges on U and W. Is this notation clear? You are just removing U, W, and some edges. So now you have a subgraph after removing. Oops, you have. Sorry. So you have a subgraph after removing U and W, right? So what can you say about the resulting subgraph H? Do you think it will satisfy Hall's condition? It will not satisfy Hall's condition?
It may or may not. In this case, it won't.
Okay, so there are two possibilities, right? Either it satisfies Hall's condition or it does not satisfy Hall's condition. Let's do the easier part first. Suppose H satisfies Hall's condition. What does it mean? Just to ensure, can somebody say what do we mean by H satisfying Hall's condition? So H is the graph that you obtain after removing U and W. You just want to ensure if you recall what it means to say that a graph satisfies Hall's condition.
Cardinality of neighborhood of a subset should be greater than the cardinality of a subset.
For every subset, right? That's
Yeah.
what we know. So now I want to use the inductive hypothesis. How many, so for that I have to see how many vertices the smaller partition of H has. So now if you look at the smaller partition of H, it has lost one vertex, right? So U minus this vertex. So I should put it this way. So this cardinality is U minus 1. Oops. And we know that this partition This partition is the smaller of the two partitions. So that is something we must remember. So we have to ensure that whenever we remove, we don't make the large partition so small generally when we want to do induction. Right? If I remove some 100 vertices, then this way will become the smaller partition. That should not happen. So a u minus 1 we know is strictly less than w minus 1. I mean less than or equal to, because u was less than or equal to the cardinality of w. So this percent, right, this set u minus u is the smaller partition. Is it clear why we are arguing this is the smaller partition? What is the use? We want to use the inductive hypothesis, right? So what the inductive hypothesis tells us is, if the graph satisfies Hall's condition, then there is a matching that saturates the smaller partition. You want to satisfy this partition, you have removed one vertex here. You want to ensure that it is still the smaller partition. Suppose in the process, during the induction, somehow you removed a lot of vertices from W, this way turned out to be smaller partition, then you cannot ensure that you match everything here by pasting things. Maybe this will be clear further by the end of the. So you know that this is the smaller partition, and by inductive hypothesis, I know that there is a matching M that saturates U minus U. So now, can someone say how to construct a matching for G from this? So this is a matching in H. Right? By inductive hypothesis, I know that H has a matching that saturates all the vertices here. So what is the matching in G?
Hello, ma'am.
Uh-huh.
Ma'am, actually, we are considering the induction on the cardinality of U, right?
Correct.
So having removed W, how can we say that by inductive hypothesis there exists a map that saturates U minus U in H? I mean, now we are no longer considering the vertex W.
Correct. So we have removed U, we have removed W also, right? So now what is in the remaining graph? The remaining graph, let's call it H after removal. Which is the smaller partition? Is it U minus U or is it W minus W?
U minus U.
Correct. So U minus U. So what does the inductive hypothesis tell you? Now you have removed one vertex. So the cardinality of U minus U. Yeah. So let's just do this. So what can you say about the cardinality of U minus U? That this is little u. So this is strictly less than k, right?
Yes.
Because you had k vertices, so you have removed one vertex. So actually the cardinality is k minus 1. So now you can use inductive hypothesis. Is that clear? You have a bipartite graph. For the inductive hypothesis, you have a bipartite graph H. Right? The vertex set is U minus U, W minus W, and there is some edge set. Let's call this E tilde.
Ma'am, but what did you exactly assume in the inductive hypothesis? I mean, for all G, U, W, E with cardinality of U less than K, if G satisfies Hall's condition, then G has a matching in W, right? I mean, the vertices with which U's vertices are connected, those are in W as a whole.
Right. Correct.
So
correct.
then, having removed small W, the vertex from W.
Okay. So you have removed this vertex, right? That is your question.
Yes, ma'am.
So you have removed this vertex. If let's say you did not think about that, is it so? Once you have assigned W to U, can you use W again? Okay, so maybe I will write it this way. I think the confusion is here. For any graph G with this H set, with U tilde this thing, G satisfies Hall's condition. There is a match. Does this satisfy? That is the set that you are interested in. The inductive hypothesis and induction are different. So now your U tilde is U minus U. Or maybe I did not understand the question. We can go over this again. What was the question now?
Ma'am, I mean, I was meaning that if we consider any set of U which is smaller than smaller in size than K, then we have a matching of
Correct.
size of that U minus U, say, and that
Right.
matching
Of that size U tilde, correct.
yes, and that matching belongs to the set W, right? I mean, all the vertices are
W
still in
tilde,
W.
right? W tilde.
Oh, okay,
Now,
okay.
yeah, I should. So now W tilde is W minus W. Now does it make Things
Oh,
clear?
yes, ma'am. Yes, ma'am. Now
So
I
yeah,
understand.
so this is true for any graph with two partitions. If the cardinality of the smaller partition is less than k and the graph satisfies Hall's condition, then we can find a match. So our whole job in this induction is to ensure that the graph satisfies Hall's condition. The easier is somehow you got lucky. You removed UW and incidentally your H, the resulting subgraph, satisfied Hall's condition. In the worst case, it might not satisfy. And then the whole story of how Hall solved this problem comes. Okay. So I hope that it is clear. If there are any questions, please ask, because this is the easiest part of the proof. Like you should understand this clear. So by induction, you know that there is a matching M prime, let's call this, in H, right? That saturates this set. So now I want you to construct a matching M in G. Can someone give me what that matching is?
This matching unit U D UW.
Is this clear? This is definitely a matching. First, it saturates every vertex in U. And it is definitely a matching because there cannot be any UV is entirely vertex disjoint from M prime. Because M prime is in H and we removed U and W in H. Right? This should be like super clear. And then let's move to the difficult case. When H does not satisfy Hall's condition. I'm not sure if I'll have time to finish this, but let's see. Is this clear? The easy case. So this is the hard case. Right? When H does not satisfy Hall's condition, what story are we going to do? So we are going to use the fact that H does not satisfy Hall's condition. So what does it mean to say that H does not satisfy Hall's condition?
There exists a subset of vertices such that the
Let me just
cardinality of neighborhood is less than the cardinality of your.
right? In which graph? So the neighborhood of X in what? That is what I want you to say. This subscript. Let's see, somebody who has not answered so far. Let's take it. H, right? Yeah. Because we are saying that H does not satisfy Hall's condition. So you must remember that the neighborhood of a vertex in G and H are different things. Okay? For example, this, yeah. So this vertex has W as a neighbor in G, but in H it will not be there because you removed W. So the neighborhood of a vertex, a set of vertices in G is different from the neighborhood of a set of vertices in H. That you must remember. Okay, so let's give this equation a name. I'm just going to call this 1. We'll come back to this. So we know that there is such a subset. Let's zoom into that subset and see, right, what is the graph. So let me just to illustrate, draw this. I'm doing this arbitrarily. Okay, so this might be not be the right way to teach it, but still, let's call this. Right, and you have some neighbors. We will put more neighbors here. This is the neighborhood. Okay. So this is X. This is neighborhood of X in H. In H also this will be the same because okay, yeah, W won't be there. Okay. So let's look at the graph G. Now let's take these two partitions, right? Look at X on one side and the neighborhood of X in the graph G. So what are you going to do? You're going to now zoom into this portion. So we are looking at the neighborhood in G. So this person will also come. Right? So we are just trying to see what was it that was in G. G satisfied Hall's condition, but now suddenly H does not satisfy Hall's condition. So this guy is somewhat the troublemaker. There are some troublemakers we have to deal with them. Okay. So we're going to look at this graph. Let's solve this graph F1. Okay, just like H, now also we have a graph. We have X on one side, we have the neighbors of X and G on the other side. Okay. So now, one thing we know is definitely the cardinality of X. Right? So let's just try to see what happens. So what can we say about the cardinality of X? Or what can we say about the set X? So we know that X is a subset. Oops. X I know is a subset of U minus U, which is again a subset of U. So I know that X is a subset of U. Now, so this is a smaller graph, right? We removed the vertex U, and then we are looking at a subgraph. So it's very likely that you can apply induction hypothesis here. H directly you could not apply inductive hypothesis because H did not satisfy Hall's condition. So we are trying to take out a graph from H and try to use the inductive hypothesis. Okay. So for the inductive hypothesis, what must I say? I must look at the set of vertices in the subset X that is contained in this U, and I must say that this is the smaller partition. And it's set the cardinality has to be less than K, then I can easily use inductive hypothesis. So from this, I know that the cardinality of X is strictly less than K. Right? Because this is K and this is K minus 1. So you could apply inductive hypothesis, but then to apply inductive hypothesis, what must you say? What is the other thing that we have to ensure? So I know that cardinality of X is less than cardinality of U. This implies that the cardinality of X is less than K. So I can use inductive hypothesis provided
But it doesn't satisfy Hall's condition.
does it? So that is something we have to see. Right? Provided F1 satisfies Hall's condition. Okay, let's see whether F1 satisfies Hall's condition. Okay. So we know that X is a subset of U. Okay. So to show that F1 satisfies Hall's condition, what should I do? Okay, so before that, let's just go back and see. So the question is, does F1 satisfy Hall's condition? So one thing we noted was this thing, right? That the cardinality of X is less than K. So we are in somewhat safe place to use the inductive hypothesis. Now I want to ask, what can you say about the partition? Like in this graph F1, is X the smaller partition or the neighborhood of X the smaller partition? Can someone say? So let's look at X. Let's look at the cardinality of the neighbors of X and G. Is this less than or equal to or greater than?
It is greater than, right?
Why is it?
Because that is what we assumed. Like, because H does not satisfy Hall's condition.
No, right? Okay. So this is
Oh,
where
sorry.
trouble
This
comes
is
in.
N and G. Okay, sorry.
So that is why you are clever. So this is where the brilliance of Hall's theorem comes in. So the subgraph that you constructed looked at X and looked at its neighbors in the graph G, not in the graph H. So in H, we know it does not satisfy Hall's condition. So we cannot do anything about it. But if we look at X and the neighbors of X in G, we know that this is less than or equal to, since G satisfies Hall's condition. Is this clear?
Yes, ma'am.
Everybody else, just once, one of you unmute and say yes. Somebody who hasn't answered so far, just to be sure.
Did we choose G in any particular way?
Sorry.
Did we choose G in any particular?
Did we choose? Sorry, the sentence was not clear to me. The
Oh,
question.
never mind. That's fine. I think
Does
I
any-
understood.
Okay. Yeah, if there are questions, please type because it was unclear. I'm also following the chat. Right. So one thing we know is that U is so this tells us that X is the smaller partition and the cardinality of X is less than K. So if we can somehow ensure that F1 satisfies Hall's condition, we'll be in a good shape to apply the inductive hypothesis. Okay. So does F1 satisfy Hall's condition? That is the question. So to show that, what should I do? I have to look at every subset S of X, and I have to argue about the neighbors of X, right? Yes, neighbors of X. Oops, sorry. No. This you must recall that it is less than. Why is that? S is a subset of X, which is a subset of U, and G satisfied Hall's condition. So for every subset of U, this should have been true. Is this clear? Yeah, if it is not clear, please stop. Okay, we don't want to like finish Hall's theorem. So we have that F1 satisfies Hall's theorem. Is this clear? That F1 satisfies Hall's theorem,
Yes, ma'am.
and there are two sets in F1. The smaller one is X. It's the one with the smaller cardinality. Its cardinality is less than K, and F1 satisfies Hall's theorem. So what do you do now?
Ma'am,
Induct.
Right. So you can use the inductive hypothesis. And what do you get? You get, let's call the matching M1 that covers or saturates every vertex in which set. So you in the goal, what we wanted to do was we wanted to find a matching that saturates every vertex in U. But what have we obtained by applying the inductive hypothesis to F1? So I will maybe write here clearly so that in the notes, maybe at least in the notes it will be clear if it's not clear now. Use inductive hypothesis on F1. So what is the resulting matching that you obtain? You obtain a matching M1. What does it saturate?
X.
It saturates X, right? Is this clear to everybody? This is like really important. You wanted to find a matching that saturates U, but you have found a matching that saturates X. Right? Okay. So now what is left? This portion you have to match. So I have matched this with the inductive hypothesis. This vertex I anyway matched UW. So there are some remaining things that I have to match, right? So this I have to match. I have to create another graph and try to use inductive hypothesis there. Okay, so this will actually take like 10 minutes, but I don't know whether I should do it now. Do you like what do you want to do? Like, do you want to go back and read this until now and then do this in the next lecture? Or do you want like finish the proof and then go back? Whichever is fine.
Ma'am, I had a question. Ma'am, will NG of X contain W?
So will it contain W? So what is X a subset of?
U.
Let's see.
Sorry, W.
Yeah. So X is a subset of U that does not contain U, right? So this is X. Let's just go back to what he's asking. So this portion is your X, and your U is outside it, right?
Yes.
It could contain W if there is some vertex here that is adjacent to it.
Okay, ma'am.
That is possible.
Okay.
But you must remember that we cannot use W, whether W is in the neighborhood or not, because you anyway matched W with U, right? Okay. So either is actually fine with me. Maybe you should take the call. It will take another 15 minutes, but Yeah, if you want to go back and visit these cases, so the only case that remains is if H does not satisfy Hall's condition, we want to find a matching for this portion.
So like I did not understand how we got the matching for X
Huh.
without using W.
So okay, so what is the question? So what did we do? We initially had two sets, and U
Ma'am, if
was
NG of X did not have W in the beginning, then it wouldn't have not satisfied Hall's condition, right? I mean, if it did not have W in the beginning, then it would have satisfied Hall's condition, right?
okay, I did not get the question. Can you repeat it slowly? If
Yeah.
what is the premise? It's difficult for me to follow so quickly. So what are you trying to say? What is the question? Is W in NG of X or not?
W is always an NG of X, right?
No, it depends, right? For example, if W was only adjacent to you, suppose this edge was not there.
Ma'am,
W
then
will not
otherwise,
be-
like it would have already satisfied Hall condition, right? The beginning itself from the hypothesis.
So which would have satisfied? So when you say it would have, there are several graphs here, right? We have G, we have H,
X,
we have
X.
So X is one set of vertices. So what do you mean by it satisfies Hall's condition? I did not get. You mean that the cardinality of X is less than or equal to the neighborhood? Is that what you're saying?
Yeah, yeah. It would have been less than or equal to NH of X, right? If W was not in NG of X.
So I will try to write the question actually. So you're saying that, so you have X, you have NG of X, and you have NH of X, right? So there are three things here.
Ma'am, I think he's saying ki, if NG of X didn't have W in the first place, then NH of X would still have the same cardinality. As NG of X. Because we only remove W, which is not in
Correct. That is right. So, right. So what, okay, I understand what he's saying. So how did we get from G to H, right? Like by how much can the neighborhood of G and the neighborhood of H differ? That is right. So if W was initially not in G of X, then W will not be in H of X also. Is that what you're saying?
Yeah, ma'am. So what I was saying was if the cardinality of NG of X, NG of X, like in the case 2, cardinality of NG of X is equal to X, and then we obtain a matching. How can we obtain a matching that does not contain W?
So what you are, I'm just trying to understand. So what you're saying is M1 will contain W. Is that what you're saying? Is that the question? So this whole thing, okay, I sort of understand what is going on, what you are trying to say. So maybe you, okay, so I will try to find this. Maybe U is not, so maybe there is some other vertex here.
Should we consider U along with X? I mean, when we are considering F1, should we take X union U and then do the same thing?
No, so U is removed. Like U, so F, when you construct F1, right, you only look at, so U is removed from F1. You don't.
Ma'am, like otherwise, I don't understand how like we can't take a matching without, for sure, like we cannot be sure, right? Like it will contain a matching
But
without
we
U.
didn't use W, right? That
So what he's saying that it might be that W is part of the matching M1. So the question is, can there be a matching? So will it be the case that M1 necessarily has to use W? That is a question.
So if you take U along with X, then it will be okay, right? Or maybe not. Like maybe I'm wrong.
But then how will you induct?
Yeah, you cannot take. So U is removed. Otherwise, there is no point of induction.
Yeah,
so
yeah.
U is anyhow removed. So that question is that approach is not okay. But maybe just that there are too many graphs and I okay, let's see whether W can be in. Yeah, so this is the case that you're asking, right? So it can be that there is an X in X that has W as a neighbor in G. Is that right? So W will be there in the. Okay, so I will just look into this and get back to you.
And it
before
has the
next
same
lecture.
cardinality as X, and G of X has the same cardinality as X.
Right. So then you will have to. It might become the case that you will have to include W in F1. That's what you're saying.
Yes, ma'am.
Right. Okay. Okay. I will just try to figure out why this cannot happen. Yeah. But this cannot happen actually, but I have to figure out. Yeah. Maybe before the beginning of the next lecture, I will clarify this.
Ma'am, like if I think we can induct even if we don't consider U, because for the case where X is the whole set without U, like maybe that is we can prove it separately.
Yeah. So the question as far as I understand is, should we look at X? X we have looked at it. We have to definitely remove U. There is no question about it.
Okay.
But this is this Ng of X or is this Ng of X minus W?
Okay, ma'am.
Should you remove W from here or not? That is a question that we have to answer. There is no choice of putting U inside X, then you cannot do induction, right? So that
Okay,
we
okay.
cannot do. So the only possibility is maybe we can remove W from the neighborhood. So we can probably consider X as one partition and Ng of X minus W as the other partition. Yeah, I will just clarify this before the next lecture. Yeah. Okay, so then.
Also, ma'am, I wanted to ask, can we not do anything like we know that Ng of X and NH of X differ by at most one,
Right.
like the cardinalities, and it was like the cardinality of Ng of X was greater than equal to, and
Correct.
now it is less than, so it must have been equal to the cardinality.
Correct. That is exactly what we will see. Right, next time. And then we have to use this fact somehow. How did we go from G to H, right? We just removed one vertex and suddenly it flipped from not satisfying, from satisfying all conditions to not satisfying. That's not possible, right? Unless the cardinalities were all equal to. Now you take this information and construct another graph and try to find a matching for U minus X. So this green portion here, separate. And then you patch together the matching. So you have one matching M1 here, you'll have one matching M2 here, and you'll have this vertex. Together will match all the vertices. That is exactly what has the X. Okay. So what you're saying is right. How did it go from not satisfying to satisfying? By just changing one. Right? Unless it is equal to this cannot be possible. That is right. So we will see that in the next lecture. I plan to finish the whole thing, but it's fine. Next time we can do this. This I will clarify. And I'm sorry. Yeah. Maybe there is some small issue. Yeah, but this I will figure out before next lecture. If there are any other questions, we can take. Yeah, so if you feel there are some topics in graph theory that you need like more revision or we should revisit, please write to us. We will. I hope the TS will also do this anyway, but still. If there are any specific topics that you think, for example, in Hall's theorem, you want to go over this again, then we can do it. So the rest of the proof, let's see in the next lecture. It's slightly involved, and it will take time. So. Okay, so maybe I will just end the recording.